The grounding electrode conductor to the water main should be a 4/0 American wire gauge solid bare copper, as per National Electrical Code Section 250.66/6. The equipment grounding conductors in each pipe need to be 1/0 American wire gauge solid bare copper, as per National Electrical Code Section 250.122. There are a few additional considerations to keep in mind. The oversized number 2 American wire gauge supplemental ground conductor should be terminated on the grounding bus in the current transformer cabinet, along with the water pipe bonding conductor and the equipment grounding conductors. The neutral conductors in the feeder should be insulated. The 1200 amp fuses are not considered overcurrent protection for the branch circuits in parallel MDP. Additional overcurrent protection must be provided accordingly, for example, circuit breakers or fuses within the panel. Let's delve deeper into the specifics of grounding electrode conductors and equipment grounding conductors. Firstly, it's crucial to understand the purpose of each. The grounding electrode conductor connects the electrical system to the earth, providing a path for fault current to flow back to the source. This helps to trip over current protection devices like circuit breakers or fuses, quickly disconnecting the circuit and preventing electrical shock hazards. The equipment grounding conductor, on the other hand, provides a low impedance path for fault current from the metallic parts of equipment back to the source. This ensures that any exposed metal parts of equipment are kept at or near ground potential, minimizing the risk of electric shock if a fault occurs. When sizing the grounding electrode conductor to the water main, National Electrical Code Section 250.66 provides guidance based on the size of the service entrance conductors. In this scenario, with 4 parallel runs of 350 kc mil conductors, we need to determine the equivalent size of a single conductor that would carry the same amount of current. Since we have 4 350 kc mil conductors in parallel, we need to find the total cross-sectional area and then determine the equivalent copper conductor size. The cross-sectional area of the 350 kc mil conductor is approximately 350,000 circular mils. With 4 conductors, the total cross-sectional area is 4 times 350,000, which equals 1,400,000 circular mils. Now, we need to find the copper conductor size that has a cross-sectional area closest to 1,400,000 circular mils. Referring to conductor properties tables, we find that this is larger than a 500 kc mil conductor, and the code requires us to follow table 250.66. According to National Electrical Code Section 250.66a, if the service entrance conductors are larger than 1100 kc mil for copper, then the grounding electrode conductor to the water pipe or grounding does not need to be larger than 3/0 American wire gauge copper. However, in this case, since we are using a supplemental ground rod, the grounding electrode conductor is sized per 250.66a. Given the information, the grounding electrode conductor to the water main should be a 4/0 American wire gauge solid bare copper, as per 250.66/6. This section covers situations where you have connections to ground rods, ground rings, or similar grounding electrodes, and specifies the minimum size. Now let's discuss the equipment grounding conductors. These conductors are sized according to National Electrical Code Section 250.122, which bases the size on the rating of the overcurrent protection device protecting the circuit. In this case, we have 1200 amp fuses in the disconnect. Therefore, according to table 250.122, for a 1200 amp overcurrent device, the minimum size equipment grounding conductor is 1/0 American wire gauge copper. However, since we have parallel runs, National Electrical Code Section 250.122c applies. This section states that where conductors are run in parallel in multiple raceways or cables, as permitted in 310.10h, the equipment grounding conductor shall be run in parallel in each raceway or cable. Each equipment grounding conductor shall be sized based on the rating of the overcurrent protective device protecting the circuit conductors in the raceway or cable in accordance with table 250.122. Therefore, each of the 4 conduits needs to have a 1/0 American wire gauge copper equipment grounding conductor. It's also important to consider the material of the equipment grounding conductor. While copper is the most common choice, aluminum conductors are permitted under certain conditions, as outlined in National Electrical Code Section 250.122b. If using aluminum, the conductor size must be increased to provide equivalent ampacity to the corresponding copper conductor size specified in Table 250.122. Remember, using solid bare copper for both grounding electrode conductors and equipment grounding conductors is a common and reliable practice, ensuring effective grounding and bonding. The oversized number 2 American wire gauge supplemental ground conductor plays a vital role in providing a low impedance path to ground. This conductor should be connected to the grounding bus in the current transformer cabinet. The grounding bus serves as a central point for connecting all grounding and bonding conductors, ensuring that all metallic parts of the electrical system are effectively grounded. It's important to make sure that all connections to the grounding bus are properly made, using appropriate connectors and ensuring that all surfaces are clean and free from corrosion. The water pipe bonding conductor, which connects the metallic water pipe to the grounding system, also plays a critical role in providing a low impedance path to ground. This conductor helps to prevent voltage differences between the water pipe and other grounded metallic parts of the electrical system, minimizing the risk of electric shock. The water pipe bonding conductor should be sized according to National Electrical Code Section 250.104a, which bases the size on the size of the service entrance conductors. In this case, since we have 4 parallel runs of 350 kcmil conductors, the water pipe bonding conductor should be at least a number 4 American wire gauge copper. The neutral conductors in the feeder should be insulated. Insulating the neutral conductors helps to prevent unwanted ground currents from flowing through the neutral conductor. Ground currents can cause a variety of problems, including nuisance tripping of ground fault circuit interrupters, equipment damage, and an increased risk of electric shock. National Electrical Code Section 310.4 requires that neutral conductors be insulated under certain conditions, such as when they are installed in the same raceway as ungrounded conductors operating at more than 600 volts to ground. However, even when not required by code, insulating the neutral conductors is generally a good practice. The 1200 amp fuses in the disconnect are intended to protect the feeder conductors from overcurrent. However, they do not provide overcurrent protection for the branch circuits in panel MDP. Branch circuits are the circuits that supply power to individual loads such as lighting fixtures, receptacles, and equipment. Each branch circuit must have its own overcurrent protection device, such as a circuit breaker or fuse. The size of the overcurrent protection device must be appropriate for the ampacity of the branch circuit conductors and the loads that it supplies. This ensures that the branch circuit conductors are protected from overload and short circuit conditions. Additional overcurrent protection must be provided accordingly, for example, circuit breakers or fuses within the panel. The selection and installation of overcurrent protection devices must comply with the requirements of the National Electrical Code. The code specifies the types of overcurrent protection devices that are permitted for different applications, as well as the requirements for their installation and maintenance. It's essential to consult the National Electrical Code and follow its requirements carefully to ensure that the electrical system is safe and reliable. Firstly, ensure proper coordination between the feeder overcurrent protection and the branch circuit overcurrent protection to prevent nuisance tripping. Secondly, consider using series-rated circuit breakers or fuses to improve overcurrent protection and reduce fault current levels. Thirdly, perform regular inspections and maintenance of the electrical system to identify and address any potential problems before they cause a failure. Grounding and bonding are critical aspects of electrical safety. By understanding the requirements of the National Electrical Code and following best practices, you can ensure that the electrical system is properly grounded and bonded, minimizing the risk of electric shock and fire hazards.